Okay, now let's move on to NAND and NOR gates. Again, we're going to do a basic review of these gates: NAND and NOR, the truth tables, the symbols, and the Boolean expressions. First, let's again just quickly recap the truth tables for the NOT gate or simple inverter, the AND gate, and OR gates. The NOT gate, or simple inverter, again passes the data to the output inverted. So if the input A is a 0, the output Y is a 1, and vice versa. There's a symbol for it, and there's the notation. Also note the alternative notations if you choose to use those. For an AND gate, remember that if any input is a 0, we're going to get a 0 out. But everything has to be a 1 to get a 1 out. And this doesn't matter if it's a 2-input gate, as in the truth table shown here, or more than 2 inputs, 3, 4, 5, whatever. All inputs have to be a 1 to get a 1 out of an AND gate. Otherwise, if anything is a 0, an AND gate will output a 0. There's the 2-input gate symbol. And again, this is expandable to multiple inputs. And there's the notation, the Boolean expression notation. Remember, multiplication is sometimes shown with the dot notation, sometimes indicated with the letters just next to each other. But either way, when we're ANDing, it's shown as a multiplication operation. And finally, our OR gate. Remember, in contrast to our AND gate, where if anything was a 0, we got a 0 out. For our OR gate, if anything is a 1, we get a 1 out. But if everything is a 0, we get a 0. So OR gate, everything has to be 0 to get a 0, but if anything is a 1, we get a 1. And there's the 2-input gate symbol. The OR gate is also expandable to multiple inputs. And the Boolean expression notation is an addition operation. Remember, addition always means OR. There are 2 more common basic logic gates, and they're derived using the NOT gate and the AND and the OR gate operations. A NAND gate, also called a negative AND, is just as the name implies, an AND gate with the output inverted. Similarly, a NOR gate, or a negative OR, is a OR gate with the output inverted. And these NAND and NOR gates are going to be considered to be universal gates because using only NAND gates, we can create NOT gates, AND gates, OR gates, or NOR, whatever we want. And similarly, using only NOR gates, we can create all the other basic types. We'll explore that a little bit here, but in later classes we'll discuss that at more length. But for now, just understand that universal gates are the NAND and the NOR gates, and that's because they can be used to create any other type of gate. And often these are produced in arrays so that they can be configured, according to the needs of the end user. So, starting with the NAND gate, we need a logic symbol. There's the 2-input version of the logic symbol. These are NAND and NOR gates, just like their AND and OR counterparts, are expandable to any number of inputs. But in this depiction, we have 2 inputs, A and B, and an output Y. But it's equivalent to an AND gate, which, remember, can be multiple inputs, with the output passed through an inverter. The Boolean expression for a NAND gate is Y equals A ANDed with B, with a bar over the entire product. That bar needs to be over the entire product, not over the individual pieces. Later, when we learn about De Morgan's theorem, we'll learn that A ANDed with B inverted is not the same as A inverted ANDed with B inverted. So it is very, very important that this inverter bar spans the entire product. And the other notation, alternative way to write it without the dot is Y ANDed with B inverted, but remember the entire product is underneath a single inversion bar. Multiply implies AND, the bar over the top implies invert, or a NOT operation. Some alternative notations, just as with the inverter before, A, B, quantity with an apostrophe, just make sure that the A and B are in parentheses, or the little tilde character with the A and B parentheses after that. And then the truth table for our NAND gate. Remember before, all ones was the only way to get a 1 out. With an AND gate, with a NAND gate, all ones is the only way to get a 0 out. If anything's a 0, we'll get a 1. If everything's a 1, we'll get a 0. So this gate is essentially the opposite of our AND gate. To get a 0 out, all inputs must be a 1. But if anything's a 0, we'll get a 1 out. And so our unique state, the state that gives us our unique input, is again the state where everything is a 1, but our unique state is everything is a 1 implies a 0 output. Our other universal gate is the NOR gate, and we have the symbol with A and B, 2 input case here with a Y on the end. And again, this is the equivalent of an OR gate being passed through an inverter, but it's drawn as an OR gate with just a bubble on the end. Remember I said that the bubble in the last node means inverted? Well, that bubble is taking the place of this inverter here and allowing it to be drawn as a single gate. The notation is A plus B with the quantity inverted. Again, make sure that the inversion bar covers the entire sum. You know, A plus B with the quantity inverted is not the same as A inverted plus B inverted. We'll learn more about that later. But for now, please make sure that the inversion bar covers the entire sum. Add implies OR. The inversion bar implies invert. But remember, it's the entire sum that is inverted, not the individual pieces. Then looking over here at our truth table, you know, with the OR gate, all zeros was the only way to get a 0 out for an OR gate. Now all zeros is the only way to get a 1 out for a NOR gate. It's the opposite of our OR gate. Before, if anything was a 1, we would get a 1. Now if anything is a 1, we get a 0. So our unique state, or that gives us our unique output, is still the same. All inputs are zeros. However, all input zeros for a NOR gate gives us an output of 1. And there's some alternative Boolean NOR notations if you choose to use those. Just again, make sure that the quantity is in parentheses, that you're inverting is in parentheses, so it's implied that the inversion applies to the entire quantity. Same thing here with the tilde character. And just like the gates they're derived from, AND and OR, our NAND and NOR gates are also not restricted to 2 inputs. We can have them as many inputs as we like, and our unique state stays the same regardless of the number of variables. So, we have another online assessment. If you would please complete that, and then we will move on to dip switches and simple inverters, a little bit more on those, and then to Morgan's theorems.